Quantum gravity, the theory that rewrites reality. For a century, our understanding of the universe has been split right down the middle, ruled by two giants. In one corner, you've got Albert Einstein's general relativity, the undisputed champ of the very big, of spiraling galaxies, orbiting planets, and the fabric of space-time itself. In the other corner, there's quantum mechanics, the wonderfully bizarre and unbelievably successful ruler of the atomic world, a freaky realm of probability waves and quantum leaps. These two theories are the twin pillars of modern physics, and in their own territories they work perfectly. The problem? They refuse to talk to each other. For 100 years, they've been at war, and this Cold War has left the universe's biggest mysteries completely unanswered. What really happens in the crushing heart of a black hole? What was the universe like in the very first microsecond of the Big Bang? Ask general relativity and quantum mechanics these questions, and the two pillars of physics just crumble. The math breaks, spitting out total nonsense and infinities. Physics literally stops working at the edge of reality. But what if there was a way to unite them? What if a radical new theory from a small team of physicists in Finland has finally found a way to broker a peace treaty? A theory that suggests reality isn't what it seems, and that gravity, the most familiar force of all, has been hiding a quantum secret this whole time. Section 1. The century-old problem. To really get the scale of this problem, you have to appreciate just how wildly different these two ideas are. General relativity is smooth, elegant, and geometric. Einstein imagined that space and time are woven together into a single fabric, space-time. Massive objects like a star don't pull on planets with some mysterious force. Instead, they bend and curve this fabric like a bowling ball on a trampoline. Planets and other objects are just rolling along those curves. That's gravity, and it works beautifully, predicting everything from light bending around the sun to the existence of gravitational waves. Your phone's GPS has to account for it just to work properly. Then there's quantum mechanics. If relativity is a graceful ballet, quantum mechanics is a chaotic rave. Down at the scale of atoms, reality gets fuzzy and probabilistic. Particles are also waves, somehow existing in multiple places at once until we look at them. And energy isn't smooth and continuous. It comes in little distinct packets called quanta. This weird set of rules perfectly describes the other three fundamental forces of nature: the strong and weak nuclear forces, and electromagnetism. Those three have been successfully united in one beautiful framework, the standard model of particle physics. Gravity is the lone wolf. The problem explodes when you need both theories at once, like in a black hole. It's an insane amount of mass, relativity's turf, crushed into an infinitely tiny point, a singularity, quantum's turf. Try to combine the equations and they just break. The smooth, continuous fabric of space-time can't handle the chunky, quantized world of quantum physics. The result is a mathematical dumpster fire. Physics has no answer. Section 2. Why is it so hard? So why has this problem stumped the world's greatest minds for a century? It really boils down to a clash of languages. General relativity is written in the language of geometry, smooth, flowing curves. Quantum mechanics is written in the language of quantum field theory, a pixelated world where forces are carried by messenger particles. The three forces in the standard model all play by the same rules. Physicists call them gauge theories. Think of it like a playbook. They all have a source, like electric charge, and they all have a messenger particle, like a photon, that carries the force. This playbook worked perfectly 3 times, but gravity, as Einstein described it, just rips up the playbook. Its source is energy and momentum itself, which messes with the very space-time that any messenger particle would have to travel through. It's a snake eating its own tail. For decades, everyone assumed Einstein's theory was the one that had to change, that it needed to be quantized to fit into the quantum world. This led to some of the most mind-bending ideas in all of science. Section 3. The contenders. The quest for a theory of quantum gravity is a graveyard of brilliant but incomplete ideas. The most famous is string theory. It says that deep down, particles aren't points but tiny vibrating strings of energy. Different vibrations create different particles, and one special vibration gives you the graviton, the hypothetical messenger for gravity. It's a beautiful idea, but it comes with a catch. It needs extra, hidden dimensions to reality that we've never, ever seen. Another top contender is loop quantum gravity. This theory takes a totally different shot, suggesting that space-time itself is quantized. If you could zoom in to the smallest possible level, you'd see that space isn't smooth, but made of tiny, indivisible atoms of space-time. Both of these theories are incredible intellectual achievements, but both are bogged down by mathematical quicksand and a frustrating lack of predictions we can actually test. The war between physics' two giants raged on, leaving the door wide open for a new challenger. Section 4. The new idea from Finland. And that's where our story takes us to Finland, to physicists Mikko Partinen and Jukka Tulkki at Aalto University. In a paper published in Reports on Progress in Physics, they propose a new theory called unified gravity. Their idea is both radical and refreshingly simple. They ask, what if we've been forcing the wrong puzzle piece? What if instead of inventing new dimensions or strings, we could describe gravity using the same playbook that worked for the other three forces? Their mind-bending claim is that gravity can be described as a gauge theory, fitting it neatly into the standard model's framework. This would finally bring gravity in from the cold and unite all four forces. And maybe the most exciting part is what their theory doesn't need. No extra dimensions, no weird new particles. It works within the known rules of physics, which could make it much easier to test than its rivals. Section 5. How does it, potentially, work? So how did they pull this off? They reimagined how gravity works at its most basic level. While Einstein's gravity is all about curved space-time, the Finnish theory suggests that gravitational interactions can be described in a flat, uncurved space-time, just like the other quantum forces. To make this happen, they introduced a new mathematical tool called the space-time dimension field. You can think of this field as a kind of translator. It allows the effects of gravity to be described using the language of quantum field theory, all based on fundamental symmetries. Their theory uses 4 of these symmetries, which are similar to the one that governs electromagnetism. This structure allows gravity to be treated as a force carried by a field, just like all the others. But the really clever part is that their theory doesn't throw Einstein out. While it can describe gravity in the flat space-time of quantum mechanics, the physicists showed that with a specific choice in their math, their theory perfectly reproduces the equations of general relativity. It's like having software that can run in 2 modes, a quantum mode and a classical relativity mode. It speaks both languages fluently, which is what makes it such a powerful potential solution to this century-old problem. This is a pretty wild idea, and if you're enjoying this trip to the very edge of physics, make sure to hit that subscribe button. We break down complex ideas like this every week, making the impossible a little easier to understand. Now, back to rewriting reality. Section 6. The implications. Rewriting reality. If this theory holds up, the implications are just staggering. First, it would give us the tools to finally understand the places where physics currently breaks down, singularities. We could ask what's at the center of a black hole or what the universe was like at the instant of the Big Bang, and get real answers instead of a mathematical error message. It could even help us begin to tackle long-standing puzzles like the black hole information paradox. Second, it's a huge leap toward the holy grail of physics, a theory of everything. The physicists behind it are cautious with that term, but a theory that successfully describes all 4 fundamental forces under one roof is pretty much it. It would be the final chapter in a story of unification that started when Newton realized the force pulling an apple to the ground is the same one holding the moon in orbit. And finally, like all huge breakthroughs in fundamental physics, the technological spin-offs are impossible to predict, but could be transformative. Your phone's GPS is only accurate because it accounts for Einstein's theory of gravity. A complete theory of quantum gravity could unlock technologies we can't even dream of today. Section 7. The reality check. Okay, but let's pump the brakes for a second. This is a very exciting idea, but it's not a proven, finished theory. Partanen and Tulke have been very clear about this. One of the biggest hurdles for any quantum gravity theory is a mathematical process called renormalization, which is basically a way to get rid of the pesky infinities that pop up in calculations. They've shown their theory is renormalizable at the first, simplest level, but they still need to prove it works for all the more complex calculations. In the true spirit of science, they've published their work as an open invitation for other physicists to poke holes in it, test it, and help build on it. And already there's healthy scientific debate and skepticism about some of its technical details, which is exactly how science is supposed to work. What this theory from Finland represents is a new path forward, a fresh hope in a quest that has lasted for 100 years. It suggests that maybe gravity isn't the stubborn loner we thought it was. Maybe it was speaking a quantum language all along, and we just didn't know how to listen. We are living in an incredible moment where a century-old war in our understanding of the universe might finally be ending. We could be on the verge of seeing the two giants of physics, relativity and quantum mechanics, finally shake hands and unite, and in doing so reveal a picture of reality far deeper and more connected than we ever dreamed possible. The script of the universe has had a missing page for a long, long time, and maybe, just maybe, we're finally about to read it.